Yeah, thank you. The group talk that you all waited for, where we will talk about dust SED fitting, and we were supervised by Frederick and Annie. So, why you should care about dust? Well, I think this is a slide that I kind of almost stole from Javier. So you might remember that he had like this slide where he said that half of the bolometric luminosity of the universe is in the dust. And this is here an example that I took from this paper there, where you have some luminosity, or maybe it's basically arbitrary unit, and plotted that against the wavelengths. And you see that the starlight gets reprocessed, absorbed by the dust, and then re-emitted in the far infrared. And you can use this to do many nice things. So for example, if you look at this problem that has been observed with Hubble, you see that there's like some protostar in the right, and you might want to know, okay, what's like the mass reservoir from which this star could draw. And you can use, for example, also here, Herschel, to use the flux at the different wavelengths to do an easy modified blackbody fit to infer the dust mass and temperature, and then you have an idea about what this is. And this, of course, also works for galaxies. And what a modified blackbody is, this will do my colleague.
Okay, so usually we use modified blackbody spectrum to simulate the emission continuum of the dust. So it's based on a blackbody spectrum, but with a factor of opacity, and also we need to scale it according to the dust mass. So here you can see the shape of it with a given set of parameters. So as an example, to fitting the observed data. So here, like we give like 5 artificial data points, given with random Gaussian noise, and under the assumption of no correlations parameters located in Gaussian distribution. So we can fit the observation data according to we can give a best fit according to our observation. So, and here you can select how the parameters is in fact the shape of the modified Gaussian, but the modified blackbody spectrum. And also like understand, because like we know like those parameters can always like sometimes influence with each other. So of course we can give an assumption that the parameters are correlated with each other and generate a series of correlated parameter space, but that's another story due to time limitation. We cannot give a very detailed.
Okay. So yeah, we started off by generating 1,000 realizations of these parameters, but of course, assuming that now, as you could see in the previous plots, because these beta parameter and this temperature parameter are both very good at modifying the slope and the peak of the blackbody spectrum at sort of far infrared wavelengths, they are degenerate. So we want to explore that parameter space, generate 1,000 realizations using these correlation coefficients. Here's a subsample of SEDs that we have. And once again, we generate synthetic in which we add an additive Gaussian noise, which is uncorrelated with the wavelength. When you add a noise to simulate something like a calibration effect. It's using a least squares fitting routine. This is a locally explore parameter space rather than going through a full range of parameters that you might think are physically reasonable. And then we can compute the uncertainties on these best fit parameters and explore the distribution of these. And my colleague is going to tell you about that.
Yeah, so here, if we go back to 1,000 points to get the best fit parameters showing in red, this distribution is has a different slope compared to the intrinsic physical distribution of these two parameters. And this distribution matches very well with the posterior distribution of Bayesian inference for a single set of data. So basically, this red distribution is influenced by the noise of the model from the inference. And to get rid of this effect, we probably have to employ hierarchical Bayesian models. And also, we can plot the distribution of the chi-square for all the fits. And we can find that for uncorrelated noise case, this distribution matches really well with the theoretical PDF of the chi-square for degree of freedom of our case, basically 2. But if we have a correlated noise case, basically you imagine you have data from a single field wheel with calibration error, for example. In this case, your chi-square distribution will poke out above this PDF distribution. Basically, it means that you're deviating from this chi-square distribution with this specific degree of freedom. So besides the empirical models, we also tried some physical-driven models like the DAS-EM. Here are the parameters you can change. For example, you can change the radiation field strength. So here, if you increase the strength, your ICD is going to have a higher value, but also the large grain size, the large grains, their temperature will increase. So you can see a peak start to show around the right-hand side of this ICD. So basically, the black body of the large grains start to move towards lower frequencies. And we also changed the grain size by fixing the radiation field. So in this case, larger grains of PAH specifically will lower the ICD at the lower frequency. And the reason for this is that, for example, if you have like really small grains, it has lower probability by getting hit by a photon. So you have time to relax the temperature of the grain toward the CMB temperature. But if you have larger grains, it has higher probability of getting hit by the photons. So eventually you will reach this equilibrium condition of a specific temperature. And if you translate this to the ICD, you will see that for larger and larger grains, you will have ICD that decreases in around the lower, around the higher frequency.
So our next goal is to understand the value of the parameters of the DAS-EM, and in particular, we can use a Bayesian approach to do that. And in order to do that, we remember briefly that the Bayesian approach is formed by a prior distribution and observational data, and all that combined lead to a posterior distribution that describes those parameters. In particular, we have done the Bayesian approach. We tested that on the MBB. That is quite simple because we have an analytical model, but we also done that on the DAS-EM model. And in order to do that, that is a bit more complex because we have a grid of SEDs, and we can sample the posterior with a Metropolis, Hastings, and CMC. And that allows us to understand the values of the parameters of DAS-EM that we can remember are the intensity of the radiation field and the abundance of the different type of grains. And we can also understand their uncertainties. And finally, as a result, we have find that different things, but among them, we can say that we have found that P1, the intensity of the radiation, is anticorrelated with the P4, that is the parameter that describes one of the type of the grains abundance, and also that P4 doesn't really converge very well to a single value as the other parameters do. And yeah, that's it. And Yeah, that's it. We would like to thank you all for the attention.
Questions?
You tried to make the fit on which object?
Yeah.
On which object did you try to make?
On an object that has been given to us from our
Yes, but
supervisor.
what kind of object is it?
It's like a galaxy. Yeah.
Synthetic data.
So for the first part, we basically simulated
Yeah.
the data by adding the noise. But for the, I'm not sure if you use the Herschel data or.
So I did with the Herschel data, I did just the modified blackbody. I didn't find the time to do it also with DustEM, but there's of course also Spitzer data available, which could be incorporated and so on.
Maybe you said it and I missed it, but the modification of the black body, is it purely phenomenological or is there some physical motivation for this particular shape?
Well, basically the modification is the opacity, that you don't assume that everything is re-radiated equally, but rather you just adjust the slope, and that slope is determined by, the dust distribution, essentially.
Okay, thank you.
Thanks.
Our group forgot, I lost track already. 5, something like that.